All right, today we're going to look at lesson 4.2, how to analyze the graphs of polynomial functions. We're going to start with the warm-up. We're looking first of all at a third-degree polynomial function. That is, of course, letter C. The graph with a leading negative coefficient, there's two of them. That is B and C. If you look, B goes down and C goes down as on the right side of the graph, so that's how we know it's a negative leading coefficient. Domain and range of all real numbers. Domain and range, all of them have a domain of all real numbers. There's only two that have a range of all real numbers. That means it's going from negative infinity up to positive infinity in the y values, and that is A and C. The following in behavior as x approaches infinity, f of x approaches infinity. So as we move to the right, the arrow is pointing upward, so that would be A and D. And then the only one with no real zeros is graph B. So hopefully all of that was a review for you. Okay, so next we're going to look at what's called the location principle. The location principle says that if the value of a polynomial function, f of x, changes signs from one value of x to the next, then there is a zero between those two values. And that is the location principle. So suppose y equals f of x. So the blue line here represents a polynomial function. A and B are two real numbers, so A and B are both x values. And f of A is less than 0, so it's below the x-axis. F of B is greater than 0, so it's above the x-axis. Now, because this is a polynomial function, that means it's continuous. It's not like we can pick up our pencil and skip over the x-axis. So that means to get from point A to point B, or in this case, from point A, f of A, to point B, f of B, it has to go through the x-axis at least once on its way there. So that's how we know there's at least one zero between them. Now, let's look at how to locate the zeros of a function from a table. So determine the consecutive integer values of x between which each real zero of f of x equals x to the fourth minus 2x cubed minus x squared plus 1 is located, and then we draw the graph. So first step is to make a table. Because f of x is a fourth degree polynomial, it will have as many as 4 real zeros, or even it could be possible that there's none at all. But we see from the table that when our x switches from 0 to 1, our f of x switches from positive 1 to negative 1. Okay? And if you keep noticing, when our x is 1, f of x is negative. X is 2, f of x is negative. But when x goes to 3, our f of x is positive again. So that means that there should be zeros between x equals 0 and x equals 1, and between x equals 2 and x equals 3. So we're going to use the table to sketch the graph and find the location of the zeros. So at negative 1, 3, we have a point. At 0, 1, there's a point. At 1, negative 1, there's a point. At 2, negative 3, there's a point. And then the next one is at 3, 19. So the way this is going to work is it comes down like this. And then there's like a twist here at that point. And then we go down there. And then it comes straight back up like that. So our sketch of our graph is going to look something like that. And you'll notice that, like we said, there's a 0 between 0 and 1, and another 0 between 2 and 3. So our graph proves that those are correct. And we can actually use a graphing calculator. If you're not sure how, just come and ask me and I'll show you how to find exactly where those zeros actually are. Next, we're going to look at the extrema of polynomials. Extrema occur at the relative maximum or relative minimum of the function. So point A here is a relative minimum. It's lower than the points around it. It's not the absolutely lowest point of the graph, but it's lower than the points directly to its left or right. Point B is a relative maximum. Again, it's not the highest point of the graph, but it's higher than the points around it. And both points A and B are considered extrema. The graph of a polynomial of degree n has at most n minus 1 extrema. So that's important to remember. It means that if we have a third degree polynomial, at most it's going to have 2 extrema. If we have a fifth degree polynomial, it would have at most 4 extrema. Okay, so just remember that as we move forward. So we can graph a table x cubed plus x squared minus 5x minus 2 and estimate the coordinates at which the relative maxima and relative minima occur. In order to do that, I'm going to show you, you're going to use, I use a graphing calculator. It makes things a lot easier, but you do not have to do that. You can just run different values of x through for x in the function and then get a y value out of that. But to save us some time, I have used a graphing calculator and made up a table myself that I'm going to transfer onto the screen here. So I'm going to go from -4 to 3. So when I run -4 through the function, it has a value of -30. -3 has a value of -5. -2 has a value of 4. -1 has a value of 3. 0 has a value of -2. 1 has a value of -5. And 2 has a value of 0. And 3 has a value of 19. So obviously -4, -30, that's going to be way off the graph too far down below. But -3, -5, I can plot that point. -2, 4, I can plot that point. -1, 3, I can plot that point. 0, -2, I can plot that. 1, -5, and then 2, 0, I can plot that. So the way this is going to work, so we're going to come in up this way through that point, up through here, then we're going to come back down through there. So our graph is going to look something like that. Now, we can estimate that there's going to be an extrema around the x value of -2, and I can tell that from the table too. If you look at the table, you'll notice that as I'm looking just at the f of x values, start at -30, then I go up to -5, then I go up to 4, but the next one is 3, which is lower than 4, which means somewhere between the x values of -2 and -1, I've turned around. So there's a relative maximum somewhere around the x value of -2. And then as I look again at the table, so 4, then it goes down to 3, down to -2, down to -5, but then it goes back up to 0. So around this x value of 1, there's also a turnaround point. So the relative maxima has an x value of -2, the relative minima has an x value of 1. And of course we could use the graphing calculator to find the extrema of the function and confirm our estimates. Next, we're going to use another table. So again, I'm going to use my graphing calculator to program this. -x to the 4th minus x to the 3rd plus 5 x squared plus x minus 3. And then I'm going to do second and table. And for these, I'm going to make a x and a f of x table. Start with -3 and go through 3. So -3, -2, -1, 0, 1, 2, and 3. So -3 has a f of x of -15. -2 is 7. -1 is 1, 0 is -3, 1 is 1, 2 is -5, and 3 is -63. Okay, so we don't need to graph this. We can just kind of estimate where the turnaround points are. So if you were to look at the table, every point to the left of -3 is like way far negative, like -4 is at -119. So we're going up on our way towards what we have here. So when we go from -3 to -2, it goes up from -15 to 7, but the next point after 7 is lower. So we actually are going to have a turnaround point right there at -2, 7. And then I'm going down. 1 is lower than 7. -3 is lower than 1. But then there's another turnaround point because 1 is higher than -3. So that point there has to be a turnaround point. And then I go up to 1, but then I'm going back down again. So we have another turnaround point right there at 1, 1. So we actually have 3 turnaround points. This is a 4th degree function, so we can have 3 turnaround points. And I actually made a mistake here. This should be the relative maxima, and this should be the relative minima. All right, and so the relative maxima occur near x values of -2 when it was at 7 and x value of 1 when it was at 1. And the relative minima occur at the x value of 0 when it was at -3. All right, so that's how we can tell where those are just from the table. And then if we wanted to verify that, we could just use our graphing calculator and press graph. And you see that we have a graph that looks similar to that shape. And like that. And so our x value of 2 is where our maxima is, and x value of 1, there's a maxima, and then x value of 0, there's a minima. And that was what the graph looked like on our graphing calculator, and that's what we could tell from the table. All right, the next thing we're going to talk about is how to analyze a polynomial function. So the total number of certified pilots in the United States is approximated by f of x equals all of that mumbo jumbo minus another really small decimal x cubed plus 0.762x squared plus 6.317x plus 7.708, where x is the number of years after 1930, and f of x is the number of pilots in thousands. We're going to graph the function and describe its key features over the relative domain. So the first step, graph the function. We make a table of values, which we've already done here, and plot the points and connect them with a smooth curve, which we've already given you the graph in the table. All right, so the next thing we're going to do is analyze. So we're going to look at the key features in terms of the context. So what is the domain? Well, technically, the domain of any polynomial function is negative infinity to positive infinity. But this is real life, right? And so we are looking at a real life situation, a real life scenario. So we obviously, the polynomial is only accurate of describing the number of pilots after 1930. So years before 1930, the polynomial doesn't work, and it definitely doesn't work if you look at what happens before like planes were invented. So like before Orville and Wilbur Wright, there were no pilots, or at least none that were successful. So our domain really, we're just looking at from 1930. Well, they said 1930 is year 0, so we're looking at the domain is from 0, and technically it goes towards positive infinity. Eventually, though, at some point, we probably will stop using airplanes and stop having pilots, and who knows, maybe we'll develop teleport technology, or maybe we'll all have flying cars, or who knows how we'll get around at some point. But at some point, we're going to stop needing pilots to fly us around. The range, again, because we are looking at, our domain is limited from 0 to infinity, our range is going to be limited as well from 7.708 up to positive infinity. And again, we probably never will have an infinite amount of pilots, but at some point we're going to stop needing pilots to fly us around. All right, so the extrema, relative maximums, relative minimums. So we have an extrema somewhere around 50 years after 1930. You see that spot there on the table, or that spot there on the graph is relatively higher than the points around it. So because of that, we have a relative extrema at x equals 50. And then we also have a low point. You'll notice that 90 years after 1930, so in 2020, there was a relative low point. So x equals 90 would be the other extrema. And you can see that on the graph as well. So the end behavior of this graph is as x approaches infinity, f of x approaches infinity as well. So as x goes to the right, f of x is going to be going up. Technically, we could talk about the end behavior on the left side. As x approaches 0, f of x approaches 0. Or actually, as x approaches 0, f of x approaches 7.708. But we really don't need to worry about the left side of the graph here. The intercepts. Well, when the y-intercept is going to be 7.708, so we'd say 0, 7.708. That's the y-intercept. And this actually has no x-intercepts. So this graph never will touch the x-axis. Now, is it reasonable or unreasonable to assume the trend will continue indefinitely? Well, I don't think that for the rest of human history we will be using pilots. I think at some point we will develop technology to where pilots become obsolete, kind of like we no longer need to have somebody drive us around. We can drive ourselves in a car. So I think it is unreasonable to believe that the trend will continue indefinitely. At some point, we will no longer use pilots. At some point, the demand for pilots will go down, and the graph will no longer work for us, and because it's a real life situation. All right, so let's look at this last example. We're average rate of change, and I believe there's some questions like this on the homework. So the Ares 5 rocket was designed to carry as much as 75 tons of supplies and 4 astronauts to the moon and possibly even to Mars. The table shows the expected G-force on the rocket over the course of its 200-second launch. Part A says find the average rate of change. So the first thing we're going to do is we are going to sketch the graph and estimate the average rate of change of the acceleration. Then we can check our results algebraically. So when we are looking at average rate of change, we look at the first point and we look at the last point and we look at the difference between them. So the first point has a y value that is about 0.9 less than the end point. So the change in y values is about 0.9, and the change in x values is 200. So the rate of change is about 0.9 over 200, or 0.0045. And we can check that algebraically. We can do 2.2 minus 1.34 divided by 200, and we get 0.0043. So the slope of the line that connects these 2 points would be 0.0043 per second. So from 0 to 200 seconds, the average rate of change in acceleration was an increase of 0.0043 Gs per second. So that is how we can check and figure out the average rate of change. So we just look for the slope of the line that connects our endpoints, our starting point and our final point. All right, that is how we do average rate of change, and that is how we interpret the graphs of polynomials. If you have any questions, please shoot me an email or a Canvas message, and I'll get back to you as soon as I can. Have a great day.